For our reactions project, we decided to work out problem 5-13b from the textbook. In the problem, we are given a reaction that produces dimethylamine from methylamine. The reaction is given right here. We have 2 moles of methylamine going to 1 mole of dimethylamine, and the heat of reaction is negative 19.58 kilojoules per mole. In order to understand this reaction, we drew a picture as shown, in which you have the incoming mole flow into a packed bed reactor filled with silica alumina catalyst. In order to do our equation writing, we are going to simplify the reaction in terms of A, B, and C, as shown at the bottom. We have 2A goes to B and C. Now that we have stated the problem, we can start with part A of the problem, which states to write the mole balance of our reaction. If we recall from chapter 2, the mole balance for PBr can be written as FA naught dx over dw, which is equal to the rate law in terms of A, which is in our case in terms of methylamine. Now that we have done part A, part B asks us to write the rate law in terms of partial pressures. So in order to write the rate law, we need to keep in mind that our reaction is reversible, meaning that we have a forwards K and a backwards K. So now that we have that, we can write the rate law for the forward reaction, and we can write the rate law for the reverse reaction. And this is all going to be in terms of partial pressures. Once we have that one, we can find the net, which is just adding the reverse with the forward. And after we add them, we get this reaction as the net rate law. As we can see, the rate law is only in terms of partial pressures. Now that we have written the rate law in terms of partial pressures, part C asks us to set up a stoichiometric table for this reaction. So to start off, we recall the symbols that we use for each species. And the symbols are A, B, and C. And let's write the initial amount that we had coming into the reactor. So for A, we have FA naught. For B, we have 0. And for C, we also have 0. Next, we write the change that occurred. And if we remember, in order to write the change, we have to rewrite the reaction by dividing by the stoichiometric coefficient of the limiting reaction, which in this case is 2, and we end up getting this reaction. And this is how we will write our change. So for FA, we have negative FA naught times the conversion. For B, we have positive FA naught conversion divided by 2. And then finally for C, we have the same thing as we had for B, positive FA naught x divided by 2. Now we can proceed to write what we have remaining. And for us, for FA, we'll have FA naught 1 minus x. For FB, we will have FA naught x divided by 2. And for C, we will have FC FA naught x divided by 2. And this is our final stoichiometric table. After creating the stoichiometric table, we see that part D is asking us to write the partial pressures of the species in terms of conversion. And to do this, we should recall that the concentration of a species is equal to the partial pressure of that species divided by RT. And this we get from the ideal gas law. Knowing this, we also need to take into account the general equation that we use in gas flow systems for concentration. And this can be written as Ci is equal to part over 1 plus epsilon x, and of course the change in pressures as well as the change in temperatures. But for our reaction, it is being carried out under isobaric and isothermal temperatures, which means that for both of these, they equal 1. And once we have that, we can find out what the epsilon is equal to. And it's equal to the mole fraction in the vapor, theta. We know it's pure feed, so that's 1. And this is going to be -1 plus 1/2 plus 1/2, which when we do the math, we find that this is equal to 0. And this is helpful because it allows us to simplify the equation. And we end up just getting C, the species, equal to Ci naught x. We end up getting this equation for each species. And when we plug in the values, we get the following equations for the concentration of each species. For Ca, we have that as equal to Ca naught 1 minus x. For Cb, we have that equal to Ca naught x over 2. And then for Cc, we have that equal to Ca naught x over 2. And this is concentration, but to remember that it wanted us in partial pressures. So we just recall the formula that we used before. Ci is equal to Pi over RT. Plug this in where necessary, and we end up with the following 3 equations. And this is the answer for part D. Part E of the problem then asks us to write the rate law solely in terms of conversion. And to do so, we have to remember back at the rate law that we created in terms of partial pressures. Now that we have the equation for partial pressures in terms of conversion, we can just plug in where they should go, and then we end up with the following rate law. This is the rate law only in terms of conversion. Part F of the problem then asks us to find the equilibrium conversion. But now that we have, we should remember that equilibrium, the rate of reaction is equal to 0. And now that we have the function for the rate of reaction, we can set the whole thing equal to 0 and move things to each side, which will end up getting the following equation. And then when we do so, we find that the equilibrium conversion is equal to 0.76. And this will be seen in MATLAB as to how it is solved as well. Part G of the problem then asks us to write out our mole balance in terms of conversion. And if we recall, we have the FA naught dx dw is equal to the rate law. And we have this already in terms of conversion, so all we can do is we can plug in and separating the variables and then integrating. In simplification, we find that the weight of the catalyst is equal to the following equation. This is the equation that we can use in order to find the weight of the catalyst required to achieve a certain conversion. But we have to keep in mind that the highest conversion that can be achieved for this reaction is 0.76. So this limits as how high we can convert. And we're going to show a MATLAB file which uses this exact function to calculate the weight of the catalyst. Here we have our MATLAB script, and we're going to go ahead and run it. So the first part of the MATLAB is just welcoming us to the thing, and it's telling us that we'll be able to calculate how much catalyst we need to reach a specific conversion. So we have to keep in mind that our feed has to be pure methylamine, and it's asking us to input the entering flow rate. So let's say that the entering flow rate is about 26 moles per second as given in the problem. So once we input that, go ahead and select it, and then next is asks us to enter in the initial pressure in atmospheres. So we're going ahead and put 18 because that is a number given in the problem. And now it asks us to input the transport coefficient using the rate law. And we ask for this because it can change according to temperature. So we're going to go ahead and use the one that's given in the problem, which is 4.25 times 10 to the negative 6. And we have that. Now we have to enter the conversion that we want to achieve, and we have to keep in mind that the maximum is 0.76. So let's say the conversion that we want is 60%, and when in decimal form, that would be 0.6. So go ahead and input that value, hit enter, and the program goes ahead and calculates how much catalyst we will need. So according to the problem, it says for the mass of catalyst required to reach a conversion of 60% is 31 kilograms. And we have to keep in mind the catalyst is a silica alumina catalyst. Now, this reaction is important because we can see that one of the products produced is ammonia. And ammonia is used in many applications, and one such application is cooling systems. But of course, there are some dangers that we can see in dealing with the certain chemicals. And some dangers that we should probably look out for are for the fact that both dimethylamine and methylamine are flammable. So this means that we most likely have to take some precautions to decrease the risk. And we have to keep in mind that these are corrosive. Not corrosive in the sense for metals, but corrosive for our lungs as well as our eyes. So these are some things that we will need to look at when we are dealing with this reaction. And this seems like this is something that can also be scaled up if we want to use it in an industrial process. This completes our walkthrough of problem 5-13 from the textbook. Thank you for listening and watching.